Hello students, today I'll be taking an important topic in inorganic chemistry. In my video today, we'll be talking about Bend's rule. In my series of videos for JEE Advanced Revision in Chemistry, this topic of inorganic chemistry we'll be doing today, Bend's rule. It's an important topic and it deals with or it helps in explaining structures of many molecules. It helps in the comparison of bond angles and bond lengths in different molecules. So let us talk about this. It helps in relating the bond angles and hybridization. So let us recall some points related to hybridization and bond angles. One point, we'll mainly talk about hybridization involving only s and p orbitals. Hybridization sp, hybridization sp2, and hybridization sp3. These are the three hybridizations, different hybridizations that involve s and p orbitals. The bond angles, the value of bond angle theta is 180 degree in the sp hybridization. The value of bond angle theta is 120 degree in the sp2 hybridization. And the value of bond angle theta is 109 degree 28 minutes in the sp3 hybridization. We all know this fact. The sp hybridization has 50% s character. This has around 33.33% s character. And the sp3 hybridization has around 25% s character. So we can relate the bond angles to the percentage s character. Okay. What relation do we have? We can see that as the s character decreases, the bond angles also decrease. The percentage s character and the bond angles are related to each other. Okay. We can establish a relation, a mathematical relation, cos theta, where theta is the bond angle, is written as s upon s minus 1, s upon s minus 1, where s is the fractional s character and theta is the bond angle, or it is also equal to p minus 1 upon p, where theta is the bond angle, s represents the fractional s character, and p represents the fractional p character. Okay. We can put the value of s in either of these three hybridizations and verify this expression. Suppose we put s is equal to 0.5, 50% s character, s is equal to 0.5, 0.5 upon 0.5 minus 1. The value will be minus 1, and cos theta is equal to minus 1, theta comes out to be 180 degree. If you put theta is equal to s character is equal to 33%, that is 1/3. If you put s is equal to 1/3, if s is 1/3, it will become 1/3 upon 1/3 minus 1, 1/3 upon minus 2/3. We'll get cos theta is equal to minus half, theta is equal to 120. We can verify this result. It's an important result. So in many molecules, bond angles are not perfect 120 or perfect 109 or perfect 180 degree. Okay. In such molecules, we say that the hybridization is not perfect sp2 or sp3 or sp, where the bond angles are more, where the bond angles are greater, the hybridization will tend to have more of s character. Where bond angles are lesser, the hybridization will tend to have more of p character. Let us do one simple example based on this, and then we'll come to the Bend's rule statement. And let us compare the stabilities of negative charge on a cyclopropyl ring and a normal propyl carbonyl. We're comparing stabilities of negative charge on a cyclopropyl ring and a normal propyl carbonyl, comparing the stability on the secondary position. Okay. How do we compare? Okay. We'll compare by using the concept of these bond angles, the hybridization depending on the bond angles. Bond angles change, hybridization will also change. Okay. Talking about this negative charge, we can say that there is a hydrogen atom and there is a lone pair on this carbon atom. Similarly, here also we have a hydrogen atom and we have a lone pair. Now let us mark the bond angles. The bond angle, suppose it is theta 1, In the bond angle, it is theta 2. In the cyclic structure, the bond angle theta 1 is 60 degree. Despite this carbon being sp3 hybridized, the bond angle is 60 degree. It has a high angle strain. The bond angle is very low. The carbon-carbon bond angles are low. Whereas in this acyclic structure, this theta 2 will be almost 109 degree, 28 minutes. So which bond angle is lower? We'll say that the bond angle in the cyclopropyl ring is lower than the bond angle in the propyl. So what can we conclude from this? Smaller bond angle, smaller value of bond angle means more p character in the carbon-carbon bonds. More p character in the carbon-carbon bonds. If the carbon-carbon bonds have more p character, then there will be more s character towards the carbon-hydrogen bond and towards the lone pair. We'll write this point. Okay. Carbon-carbon bonds have more p character. Carbon-carbon bonds have more p character. So therefore, the lone pair is in an orbital that has more s character. Lone pair is in an orbital that has more s character. So carbon-carbon bond angle is less. Smaller bond angle, smaller carbon-carbon bond angle will result in more p character in the carbon-carbon bonds. The hybrid orbitals that are forming carbon-carbon bonds will have more of p character. As a result, the hybrid orbital in which there is a lone pair, this hybrid orbital will have more s character. Okay. The lone pair is in an orbital that has more s character. And if we apply a similar logic, in the second case, the carbon-carbon bond angle is more. So here the hybridization is almost perfect sp3. Comparing with respect to the first structure, the bond angle is more. That means the p character will be less, the s character will be more in the carbon-carbon bonds. The s character will be less in the lone pair. We'll say that the lone pair is an orbital. The lone pair is in an orbital that has less s character. Okay. So for the first molecule, lone pair is an orbital that has more, in the first structure, lone pair is in an orbital that has more s character. In the second structure, lone pair is an orbital that has less s character. More s character means more electronegativity. We know that electronegativity is proportional to percentage s character. More s character means more electronegativity. More electronegativity, lone pair will be held more strongly towards the more electronegative atom. Negative charge will be more stable on more electronegative atom. So more s character results in more electronegativity. More s character results in more electronegativity. Less s character results in less electronegativity. Okay. We are talking about stability of this lone pair, stability of this negative charge. Negative charge is more stable on more electronegative atoms. So negative is more stable. And here we'll write negative is less stable. So this is a very important result. Okay. The bond angles and hybridization are related. The bond angles change, the percentage S character, percentage P character will change. Accordingly, the stabilities of negative charge and positive charge will change. So we can say that the cyclopropane, negative charge on the cyclopropyl ring is going to be more stable on negative charge on normal propyl ring, normal propyl molecule. We'll say that cyclopropane is more acidic than propane molecule. Understood everyone? Which is more stable? The cyclopropyl carbanion is more stable than propyl carbanion. And we can explain this by the relation between the bond angles and the percentage S character or percentage P character of hybrid orbitals. Okay, understood everyone? Clear? This statement is clear to everyone. This concept is clear. Which is more stable? The 1 is more stable than 2. So we have got that the cyclopropyl carbon ion is more stable than the propyl carbon ion. This is the stability order. And we have explained this with the help of the relation between bond angles and hybridization. This is a part of Bend's rule. The actual statement is slightly different. Now we'll come to the actual statement of Bend's rule. Okay. So we have understood this. Now we'll come to the actual statement of Bend's rule. Okay. We'll keep in mind this point that as bond angles change, hybridization will change. And electronegativity increases with increasing percentages factor. We'll keep these 2 points in mind. And now let us look at the actual statement of the Bend's rule. Let me rub this. The actual statement of Bend's rule is whenever we have a central atom that is bonded to two or more different surrounding atoms, central atom bonded to two or more different surrounding atoms, and the hybridization is involving only s and p orbitals. Normally, it is defined for hybridization involving only s and p orbitals. Sometimes we also apply it for hybridization involving d orbitals, but it makes more sense to apply it on hybridizations involving s and p orbitals. So when we have a central atom bonded to two or more different atoms, then the hybrid orbital that is forming bond towards the more electronegative atom, the hybrid orbital that is forming bond towards the more electronegative atom will have more of p character, and the hybrid orbital that is forming bond towards the less electronegative atom will have more of s character. Let me write this. The statement is the hybrid orbital forming bond towards the more electronegative atom has more of p character towards more electronegative atom has more p character, and that towards the less electronegative atom has more s character, and that towards the less electronegative atom has more s character. So in other words, we say that the more electronegative atom pulls p character towards itself, and the less electronegative atom pulls s character towards itself. Let us understand why this happens. Suppose we have a central atom A, and that is bonded to an atom X and another atom Y. And some other atoms are also present. Let us talk about two different atoms, X and Y. The electronegativities are such that electronegativity of X is more than that of A, and electronegativity of A is more than that of Y. Electronegativity of X is more than that of A, and electronegativity of A is more than that of Y. So if you look at the AX bond, the polarization of the AX bond will be such that X is more electronegative. So atom X will have delta minus, atom A will have delta plus. Okay. And if you look at the AY bond, on the AY bond, A is the more electronegative atom, so atom A will have delta minus, atom Y will have delta plus. Okay, understood? Now we know that the positive charge tends to be more stable on less electronegative atom, and negative charge tends to be more stable on more electronegative atom. So for greater stability of the positive charge, this atom will try to attain a hybridization with lower electronegativity. Lower electronegativity means more p character because it wants to stabilize the positive charge. And positive charge is more stable on less electronegative atom. Positive is more stable on less electronegative atom. So we'll write this point. Positive more stable on less electronegative atom. Positive is more stable on less electronegative atom. Okay. Therefore, this atom will try to have hybridization in which it has lower electronegativity. Hybridization with lower electronegativity means hybridization with less percentage S character and more P character. To stabilize positive charge, to stabilize this delta positive charge, a hybrid orbital on this atom towards the halogen, towards this element will have more of P character. So we'll say that this is more P character in the hybrid orbital. More P character in the hybrid orbital. Why so? More P character will result in less S character. Less S character will result in less electronegativity. Less electronegativity will result in greater stability of this delta positive charge. Okay? Always atoms and molecules tend to remain in the most stable state, tend to attain the stable state. And to attain that stability, the hybrid orbitals acquire different S character and P character in such a manner that this polarization is stabilized. This charge distribution results in a stable structure. And similarly, talking about bond towards less electronegative atom, the polarization is such that atom A has delta negative charge, and negative charge should be more stable on more electronegative atom. Negative charge is more stable on more electronegative atom. So this atom A will tend to acquire a hybridization in which the hybrid orbitals will have more S character. Okay. We'll say that this atom A has more of S character in the hybrid orbital. More of S character in the hybrid orbital. So it's very straightforward now. I think अब समझ में आ गया होगा ये statement. ये statement को relate करते. Let us relate this statement and look at this example. Whenever we have a bond towards a more electronegative atom, the hybrid orbital has more P character. And bond towards a less electronegative atom, Y is less electronegative than H. Bond towards the less electronegative atom has more S character in the hybrid orbital. So this is a very important result. Let us try and apply this result in some molecules. Let us look at some examples. Okay. So we'll keep in mind that the more electronegative atom will pull P character towards itself, and the less electronegative atom will pull S character towards itself. One simple example. Let us assume that, let us take a case where carbon is the central atom, and there are two hydrogen atoms bonded to it, and there are two fluorine atoms bonded to it. If all atoms are same, if it is a CH4 molecule or a CF4 molecule, carbon tetrafluoride or methane, in either of these, the hybridization is perfect sp3. But when we have two hydrogen and two fluorine, the hybridization of carbon is not perfect sp3. Why? The fluorine atoms will pull P character towards itself. So the hybrid orbitals that are forming bonds with fluorine, these hybrid orbitals will have more of P character. The bonds towards more electronegative atom have more of P character. And the hybrid orbitals that are forming bonds with the less electronegative atom, hydrogen atom, these hybrid orbitals will have more of S character. What important experimental result we can see as a result of this? An important experimental observation which we can make about this molecule, and which is a direct implication of more P character and more S character on these orbitals, the bond angles are not exactly 109 degree 28 minutes in this molecule. It is found that the bond angle between the fluorine and fluorine atom, suppose we write it as theta, and the bond angle between the hydrogen and hydrogen atom is phi. It can be shown that phi is greater than theta. Experimentally, it has been proved that phi is greater than theta. And also logically, we can say that more S character means larger bond angle and more P character means smaller bond angle. So in the CH2F2 molecule, the fluorine carbon fluorine bond angles is smaller than the hydrogen carbon hydrogen bond angle, and this can be best explained by Benz. I think I'm very clear in this. So bench rule helps us in explaining the bond angles, or sometimes it will also help us if bond angles are known, if we know the structure, it will also help us in predicting the percentage P character or percentage S character, and accordingly the electronegativities, and based on that stabilities of carbon ions or carbocations, as we did in an example before we discuss the statement of Benz rule. I talked about stability of cyclopropyl carbon ion and a propyl carbon ion. So that is also an application of Benz rule. Understood? Let us apply this rule in one example where we'll be using this rule to compare bond lengths in a molecule. Let us do a very well-known question. Comparison of oxygen-oxygen bond lengths in H2O2 and O2F2. Comparison of oxygen-oxygen bond length in H2O2 and O2F2. Let us compare oxygen-oxygen bond lengths in H2O2 and O2F2. It's a very well-known example. There are various explanations for this, but I'll explain this by using the Benz rule. Let us draw the structures. They have open book-like structures. H2O2 trochem. Similar structure is for F2O2 also. Open book-like structure. This looks like an open book where the hydrogen atoms on the two sides form pages of an open book. The fluorine atoms on the two sides form pages of an open book. Hence, we also call this structure as the open book-like structure. What do we have to compare here? We have to compare the oxygen-oxygen bond lengths. Suppose this is D1 and suppose this is D2. We have to compare the bond lengths D1 and D2. We'll use the Benz rule to compare this. How will we use? Oxygen-hydrogen bond. Hydrogen is less electronegative than oxygen. We'll say that towards the oxygen-hydrogen bond, S character will be more. So therefore, towards the oxygen-oxygen bond, P character is more. We'll say that the hybrid orbital in oxygen-oxygen bond, the hybrid orbital in the oxygen-oxygen bond have more P character. The hybrid orbitals in oxygen-oxygen bond have more P character. Why? On this oxygen atom, hydrogen is the less electronegative atom, oxygen is the more electronegative atom. Comparatively, between hydrogen and oxygen, which is more electronegative, oxygen is the more electronegative atom. So towards the hydrogen atom, the hybrid orbital will have more S character. So towards the oxygen atom, hybrid orbital will have more P character. Understood? Now if you look at this molecule O2F2, it is the fluorine atom which is more electronegative than oxygen. And towards more electronegative atom, P character will be more. So towards the less electronegative atom, S character will be more. So we'll say that the hybrid orbitals in the oxygen-oxygen bond, hybrid orbitals in oxygen-oxygen bond have more S character. Now we'll get to our result. More S character results in smaller orbitals. sp orbitals are smaller than sp2 or smaller than sp3. Size of hybrid orbitals depends on hybridization, depends on percentage S character. So more S character results in smaller orbitals. Smaller orbitals will result in shorter bonds, and larger orbitals will result in larger bonds. More S character, smaller orbitals resulting in shorter bonds. More S character, smaller orbitals, shorter bonds. And more P character, larger orbitals, longer bonds. More P character results in larger orbitals and longer bonds. So this is a very typical example illustrating the Bend's rule. Okay, so hydrogen is the less electronegative atom. Towards the less electronegative atom, S character is more. Therefore, towards the oxygen-oxygen bond, P character is more. P character more means larger orbitals. Larger orbitals means longer bonds. And fluorine here is the more electronegative atom. So towards fluorine, P character will be more. So therefore, towards oxygen, S character will be more. More S character means smaller orbitals. Smaller orbitals means shorter bonds. So the bond length order will be the oxygen-oxygen bond length in H2O2 is more than O2F2. So this is our answer. And we have explained this with the help of Bend's rule. I'll stop my video today at this point. I hope I have explained Bend's rule satisfactorily. It's an important concept, and it's sometimes not mentioned very properly in textbooks, not very elaborately in textbooks. I hope I have made it clear to you all. I hope I'm very clear and Bend's rule is clear to you all. I'll be continuing on with more topics in future videos. Thank you everyone. Thanks for watching my channel. If you like the video, please subscribe to my channel. Thank you everyone.